I started the IoTT channel almost 2 years ago with a video showing how I built a LocoNet to MQTT gateway. And quite interestingly, this very first video is still getting views. In fact, it has consistently remained in the top 10 list of my most viewed videos. It seems the MQTT topic continues to generate interest among model railroaders, even more so now than 2 years ago. So it is time to revisit the topic and see what's going on. Welcome to the IoTT channel. I am Hans Tanner. In this video I will briefly explain in layman's terms what MQTT is and how it works. Give you access to an example you can play with for yourself. Demonstrate how MQTT can be used to bridge between model railroad control systems from different manufacturers, and leave you with a question to think about for yourself, of course, until I will give you my answer in the next video. Let's get started. So, what is MQTT? Here is an explanation from the MQTT.org webpage. MQTT is a machine-to-machine Internet of Things connectivity protocol. It then goes on with terms like lightweight, small footprint code, restricted network bandwidth, subscriber model, and so on. You can study that technical stuff for yourself. I leave you some links in the description below. Here is how I explain it for model railroaders. Think about an MQTT message as a boxcar. It has a standardized size and provides space for customers to load their goods on it. And on the outside of the boxcar there is a cardboard to tack on cards with shipping directions or special instructions about the lading. In MQTT terms, we are talking about a standardized MQTT message, the payload that goes inside, and the topic that is attached at the outside and roughly says what the payload is and where it needs to go. Now, a little strange, the railroad network is organized in a star configuration with all tracks going to a central turntable, which in MQTT is called the broker, and the customers sitting at the other end of the track. And yes, every customer has its own track attached to the turntable. So when a customer wants to send something, he puts whatever it is as payload in an MQTT message, places a label on the outside of the boxcar and sends it to the turntable or broker. In MQTT, this is called publishing a message. The broker then looks at the cardboard on the outside of the boxcar and checks a list of customers who have expressed interest in everything with that particular label or MQTT topic. This expression of interest by a customer is called subscribing to a topic and needs to be done by every customer for every topic he is interested in. Now the broker kind of clones the boxcar, including payload and paperwork. Okay, that cloning may stretch the comparison a little bit, but anyway. The broker sends identical copies of the original boxcar to each subscribed customer. And yes, if the original sender happens to be a subscriber for the topic, he also would get a clone of his own message. Now each customer receives a boxcar and can unpack the payload and do whatever he wants to do with it. So it's relatively simple. And the important things to remember from this analogy are right here. And finally, what is needed to send and receive MQTT commands from our model railroad control bus? Well, one of the customers in the freight network needs to be equipped with a small crane that can move the payloads between the cab control network and the MQTT network. In IT terms, this crane is called a gateway, and is what I made my very first video about, a LocoNet to MQTT gateway, which can transfer LocoNet messages to the MQTT network and vice versa. In the meantime, such a gateway has become an integral part of every IoTT stick. Okay, enough theory, let's do a little demonstration. On my computer, I am running a special MQTT client that makes it very easy to create MQTT messages. That software is called Node-RED and allows for graphical programming of message flows, which I used to create this example. At the beginning of the demo flow is a trigger node that sends a trigger command every 5 seconds. I feed it into a random function which randomly selects one of 3 outputs. The first output generates a switch command, the second a signal aspect command, and the third simulates a block detector input. This functionality is programmed in the form of small JavaScript code snippets inside of each node. Let me show you some code examples so you can understand the inner workings. You can also download all nodes of this example from my GitHub page and import it into Node-RED once you have it installed. First, the random generator node. I double-click it to open the function editor. Here's what it does. First, I call the random generator, which returns a value from 0 to 1, but 1 not included. I multiply it with 3 and truncate everything after the decimal point, so the possible results are 0, 1 and 2. Next, I define the topic of the message as randgen, but that's actually not even needed. Finally, I send the message to one of the 3 outputs of the function, based on the value. So every time this node is triggered, which is every 5 seconds, the trigger message is forwarded to a randomly selected output to generate either a switch, signal, or block detector message. Let's now open the switch simulator function node as an example. First, I create 3 random values for switch address, switch position, and the LocoNet command type I want to use. Remember, the LocoNet system has this push bit, which allows to block regular switch commands. So if the push bit is set and I want to operate it anyway, I need to send a switch acknowledge command instead of the normal switch request command. In this first line, I make a random selection which command is going to be used. In the second line, I randomly pick a switch address from 1 to 4, and in the third line, I randomly set the switch direction to thrown or closed and the coil status to on or off. In line 6, I put all this data into the message payload and send it to the next node in line 7. So I think you get the idea. The next node sends switch LocoNet, then creates the final LocoNet message format according to the definitions in the LocoNet PE document. Now the boxcar is loaded, so to speak, and is sent to the broker. In fact, I send it to 3 brokers simultaneously, so that you have something to play with, because IoTT Hive and IoTT Mosquito are public brokers that sit somewhere in the cloud. That means you can access them and see the commands flowing. To do so, you need to install an MQTT client on your PC or cell phone. There are dozens of free programs available. On a PC, you can, for example, install a program named MQTT Box, which is available for Linux, Mac and Windows. I place a link in the description below. For a cell phone, you go to the App Store and search for MQTT Client, which gives you a list of programs. Once you have a client installed, you set it up for one of the public brokers, either testmosquito.org or broker.hivemq.com. The port is 1883 and username and password fields remain empty. Next, you subscribe for the IoTT LN broadcast topic and voila, you should see the messages coming in every 5 seconds. If you want, you can do the same on a second and third and whatsoever computer, and you see the same messages arriving simultaneously on all connected nodes. Now, if you happen to have an IoTT stick, you can set it to receive LocoNet commands via MQTT and set the MQTT configuration to the same broker and topic. When you now open the LocoNet viewer on your PC or you cycle the stick screen to LocoNet viewer, you see the messages flowing as well. And to make it real practical, you next can connect the LocoNet communication module to the IoTT stick, configure the IoTT stick as LocoNet to MQTT gateway, and you see the messages being transferred to your local LocoNet, and something gets activated every 5 seconds as my computer plays with your layout. And it actually works in both directions. With the gateway activated on the IoTT stick, any command created in your local LocoNet will be sent to the MQTT broker and to all connected clients that are subscribed to the LN broadcast topic. So now that you understand the basics of how MQTT works and how commands from your layout can make it to anywhere in the world, you may ask yourself, what is this actually good for? Well, to get an idea of that, let's go straight to the GitHub page of fellow model railroader Richard Hughes, who is also the initiator of the MQTT for Model Railroaders discussion forum on IO groups. On his wiki page, he shows a glimpse of what is possible. Essentially, we can look at MQTT as a network backbone that makes it relatively easy to add all kinds of sensors and actuators and other devices and use them for the model railroad. The model railroad becomes an IoT device, so to speak. It becomes possible to use relatively cheap standard components instead of system-specific devices from your favorite control system manufacturer. For example, using your cell phone as throttle, your tablet or big screen TV as CTC panel, or dimming the lights of your layout room based on the fast clock time of your system using just off-the-shelf components. So that is exactly the same approach I am using with the IoTT stick, which can morph into several device types depending on the connected head module and has a built-in Wi-Fi MQTT connection, so it can either serve as standalone MQTT end device or even as gateway if connected to a LocoNet or OpenLCB interface module. But it does not end here. The second area I see is that an MQTT network also provides an ideal location to run layout-related logic. Basically everything that is producer or consumer of layout control messages. For example, in video number 47, I demonstrated the 2-button directional activation of routes using the button handler module that is part of the IoTT stick. Well, that logic can be anywhere in the network, and in an extended MQTT network it could be easily implemented in a Node-RED component with a few lines of JavaScript code, because all it does is listen to incoming button messages and then send out a sequence of switch and signal messages. The command station in this example does not care where they are coming from. And the third important area of application I see for an MQTT network is bridging between model railroad control systems from different manufacturers. I have demonstrated this in video number 45, where I used an OpenLCB I/O board to activate a switch on the LocoNet layout and switch input on the Digitrax throttle to control an LED on the I/O board. The code to do that is very simple, and again I have used Node-RED to implement it. In the first event chain, I listen for OpenLCB topics received from the OpenLCB to MQTT gateway. If a message is received from the OpenLCB producer I am watching, it gets reformatted to a LocoNet message and then sent to the LocoNet to MQTT gateway, from where it makes it to the LocoNet network. And the second chain does it the other way around. All the two nodes do is translating the incoming command and address to a format that the other system understands. For this video I thought about another example that you can try for yourself. If you are using JMRI, you probably know that it also has a built-in MQTT connection feature, although at this time it is still limited to switch commands, but that's good enough for an interesting test. Here is what you do. Open JMRI Panel Pro and activate the MQTT connection. Use test.mosquito.org as broker and IoTT bridge as master topic, which is called channel in the JMRI setup. Note that you need to start Panel Pro as administrator or it will not be able to activate the MQTT connection. This is a bug in the JMRI software and it seems it is being worked on. It might even be fixed by the time this video gets published. After restarting Panel Pro, you open the Tools Turnout control window and then the MQTT client as you did before. You now can enter a switch address and click Thrown or Closed and you will see LocoNet messages appear in your MQTT client. And if you have an IoTT stick with the LocoNet to MQTT gateway active, you are able to control the turnouts on your layout. How does this work? Let's have a look. When you click the Thrown or Closed button, Panel Pro publishes a message to the Mosquito broker. I have my Node-RED system subscribed to the JMRI switch topic, and so it gets that message and passes it on to a function that extracts the switch number and the position and puts it in the form we have seen earlier. This new message is then converted to a LocoNet format and sent to the public brokers using the IoTT LN broadcast topic as before. And since your client is still subscribed to the topic, you see the message showing up on your screen. I find it interesting to observe the latency as the message travels twice through public servers. The Mosquito server is probably located in North America, most likely in Canada, while the Hive MQ server appears to be in Europe. So the message goes from your JMRI computer to Mosquito in Canada, then to the Raspberry Pi in my office in South Carolina, which runs Node-RED, then to the Hive MQ broker in Germany, and from there to your MQTT client, and all that in about half a second. I think that's quite impressive, and for sure I would be interested to hear what latency you get from your location. Please let me know about your results in the comment section below. So, are you getting excited? Well, not too fast. One area that certainly needs to have a broader discussion is how to structure the topics and what information to put into the payload and in what format. Let's have a closer look into the structure of the MQTT messages from JMRI, Richard Yu's suggestions, and the IoTT stick implementation to understand the differences. If you click Thrown or Closed in Panel Pro, you get the following message. Using Richard's message structure, the same message would look something like this. Note that this example is somewhat theoretical as it is the specification from Richard's GitHub page. To my knowledge, there is no published prototype software at this time to play with. And from the IoTT stick, you will see this. That does not exactly look like any of these are compatible to each other. The JMRI message has most of the information in the topic string, including the address of the switch to be operated. The payload itself only has a string with the requested position. Richard's message structure has the command type and some geographical information in the topic. The payload is using a JSON string, which is state-of-the-art in IoT messaging, because it makes it much easier for decoding the individual message elements. Content-wise, it has a message type, some message-related information like version, timestamp, session ID and node ID, which appears to be the sender of the message. And then the command data itself, port ID probably being the switch address and the desired new status. In Richard's application specification, he also defines a response to the message, so the receiving node is supposed to confirm the execution of the command, which with the available DCC hardware in most cases is only a confirmation that the message has been delivered to the CAP network, but no guarantee for successful execution. This of course may change with future hardware. The IoTT stick is on the other extreme of the spectrum, as there is only one topic for all broadcast messages. As in Richard's solution, the payload is a JSON string with some message-related elements like sender, timestamps, request ID and error flags, which is primarily used by the gateway. The actual switch and position data is simply an encapsulated LocoNet message data array, or a GridConnect encoded OpenLCB data array in the case of an OpenLCB message. So, what is the best approach and what information should be part of the MQTT topic and what should definitely go into the payload? That's my homework for you to think about, and I am interested in your opinion. I will discuss this further in the next video and then also give you my reasoning for selecting the single topic approach for the IoTT stick after looking into a good number of other possibilities. I am sure if you watched until here, you don't want to miss this discussion, so it would be a good idea to subscribe to the IoTT channel and click the bell icon so you are in a premium seat when the next video comes out. And if you found this video helpful, useful or at least interesting, please click the like button while you are at it. It helps to promote this video and the IoTT channel in general, because YouTube likes the likes. Thank you. And that's it for this video. Thanks for watching and see you next time.